Okay. Hello. 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 Hello.
Good evening, sir.
Good evening. Okay. Today is period number 5, right? Topology. Okay. See, when you don't speak to me, you please unmute because some students are finding noise. Okay. If you don't speak to me, please unmute. What is your, please mute. If you don't speak to me, please mute. Right? Yeah. So today I'll start with the concept of connectedness. Okay. Connectedness. Yesterday, we were talking about separation. Right? We studied T1ness and then T2ness and then regularity, right? And then complete regularity. Okay. We studied about a property each of these 4 concepts. Today, let's discuss a little about connectedness, right? Say you have a topological space X comma tau. I hope I'm audible to everybody. Hello?
Yes, sir.
Yes, sir.
You're able to see the whiteboard,
Yes,
right?
sir. Yes, sir.
Yes, sir.
Okay. If you have any difficulty, please send me
Okay,
message,
sir.
right? Through chat box, you can send me message.
Okay, sir.
Okay. Let X2 be a topological space, right? Let X2 be a topological space, right? If X can be written as capital A union capital B, where A and B come from, where A and B come from the topology tau, and they are non-empty. A is non-empty, and B is also non-empty, and their intersection is empty. Okay, right? And then we say X is disconnected. We say X is disconnected. Okay, means whenever we can write a topological space X as a union of 2 disjoint open sets, open non-empty sets, right? Then that space is called a disconnected space, a disconnected topological space. Otherwise, we say it is a connected space. Whenever it is not a disconnected space, we say it is a connected space. Means if we cannot write X as a union of 2 non-empty open disjoint sets, then we say that space capital X is connected. Okay, so you can put it in words, right? Okay, so capital X, topological space X comma tau is a topological space. This is definition. A topological space X comma tau is said to be connected if it cannot be written, it cannot be written or expressed as a union of two non-empty, open, disjoint sets of it, subsets of it, of course, subsets of it. Okay. A topological space x comma tau is said to be disconnected. A topological space x comma tau is said to be connected if it cannot be written as a union of two non-empty, open, disjoint subsets of it. Okay. So whenever this is not possible, this is called a kind of separation. Okay. This can be called a disconnection. Whenever this is not possible, we say capital X is connected. Sometimes we also call capital A, capital B separated sets. Okay, we say this is a separation, and we call capital A, capital B a separation for X. Okay. In R, if you in R, if you take the usual metric, modulus metric, the Euclidean distance metric. Okay. Under this metric, it is if you look at the usual topology on R, the only connected subsets of R are intervals. Here in this topology, right? The only connected sets are intervals, right? The only connected subsets, right? See. Here we defined connectedness for a topological space. And if you take a subset, you have to look at the subspace topology on A. If you take a subset of R, you have to look at this has a topology, the usual topology, this metric, Euclidean distance metric induces topology. Corresponding to this, you take the subspace topology here. You intersect all open sets here with capital A. You get to a topology here. That is called subspace topology. So with respect to the subspace topology on A, we can speak of its connectedness. Okay. So so for R, if you take the usual Euclidean distance metric, and if capital A is any subset of R, then A is connected if or only if A is an interval. Okay. So the only connected subsets of the number line are intervals. Those may be open intervals. Or semi-open intervals. Okay, those may be semi-open intervals, or right. There may be open intervals, or left open, right closed, or right left closed, right open, or closed intervals. Okay, these are the four possibilities for A to be an interval. So the only subsets of capital R are intervals, and R itself is an infinite interval. Okay, R is an infinite interval. Okay, that's how R becomes connected. Okay, this is something about the connectedness of R. Sir, please page number. No, you look into the concepts on right. What? I am not looking into the book. It is page 118. It is from the chapter 118. Okay, I am not looking into the book. Okay. Yeah. Right. Now, let us look at this question 8a. Let us look at this question from the 2019 paper. This is 8a. 8a. Prove that any continuous image of a connected space is connected. Continuous image of a connected space, a connected space is connected. Okay. Right. I'll give you the page number. Of course, I don't look into the book and try to explain without looking into the book. Page 118. What is there may be a result on this. What is this thing? Give an example of line theorem. Yeah. That is 14.14.1. It is 14.14.1, page 121. Okay, right? Right. Continuous image of a connected space is connected. So let x comma tau and y comma some new be topological spaces. Okay, and f mapping x into y be continuous. Right. So remove this. Right. So let us start with two topological spaces, x comma tau and y comma eta. On y, eta is a topology. So let us take two topological spaces, and here I take tau and here I take eta. Right. And let f map x into y continuously. Okay. Now a continuous image of a connected space is connected. Let us also assume that x is connected. Let us assume that x is connected. So let x be connected. Okay. And f map x into y be continuous. So we are assuming connectedness for this. And this x is taken to what? F of x. Okay. Our claim is that this f of x is connected. F of x is connected. Okay. This f of x is a subset of y. There is topology eta on y. So from eta, this inherits a subspace topology. You intersect the open sets in eta with f of x. You get the corresponding topology on f of x. Okay, that is the subspace topology induced from eta. Right? We have to show that under the subspace topology, f of x is connected. So let us start with negation. Let us assume that f of x is not connected. Let f of x be not connected, means disconnected. Let f of x be disconnected, means there will be a disconnection. There will be a disconnection for f of x. What does it mean? F of x can be written as union of two non-empty open sets, right? F of x, capital F of x can be written as two non-empty open sets where a comma b are from the subspace topology on f of x, right? And they are non-empty. They are a comma a is non-empty and b is non-empty, and that they are disjoint. Okay. Now, what kind of open sets do exist in f of x? They are intersection of f of x with open sets in eta. So A will be f of x intersection some g, and B will be f of x intersection some h, where g and h are coming from eta, and g and h are non-empty. G is non-empty and h is also non-empty. Okay, and that they are disjoint. Right? This we are assuming that f of x is disconnected. Okay, so there will be a disconnection for f of x. Where does f of x lie? F of x lies in y. So as a subspace topology, f of x is disconnected. As a subspace, as a topological subspace, f of x is disconnected. So you have f of x is equal to A union B, where A and B are open sets in f of x, and they are non-empty and they are disjoint. Okay, and what kind of open sets do lie in eta suffix f of x? They are f of x intersection open sets in eta. Okay, so they are f of x intersection G and B of x intersection H, where G and H come from eta. This is the topology on Y. Okay, because A is non-empty, B is non-empty, your H and G also will be non-empty. H and G will be non-empty. And because A and B are disjoint, these two are disjoint, your G and H will also be disjoint. Okay, f of x is common in these two, so G and H has to be disjoint. Okay, now if you take the inverse image of this, what happens? X becomes F inverse of A union B. X is, what is the problem? Yeah, X is F inverse of A union B. Now this can be written as F inverse of A union F inverse of B. Okay, you can verify all these are correct. From here, you can write X is F inverse of this, then the F inverse of this union is union of F, individual F inverses. Okay, now what is A? It is F of x intersection G. This is F inverse of F of x intersection G union F inverse of what is B? F of x
intersection H.
Intersection H. Okay. Now this can be shown to be equal to x intersection F inverse of G, right? Union. Here it is what? F inverse of F of x. This is H. I'm sorry. This must be H. This is H. So, right? In place of B, I'm taking F of x intersection H. So F inverse of this will be x intersection F inverse of H. This is F inverse of H. Okay. It's a kind of De Morgan's law, right? A distributive law. Okay. This union will be coming here. Now, because x equal to x intersection this, right? You can show that this is equal to F inverse G union F inverse H. Okay, right? You can show that x equal to this one, x intersection this, of course, right? This is subset of this. So the F inverse G, F is mapping x into F of x. Of course, F of x is sitting inside Y, right? So G and H are taken here. G, F contains G, comma H, right? G and H are subsets of Y. So F inverse of G will be subset here. F inverse of H will be subset here. So, right, x intersection this. Each of these is subset of this. So x intersection this will be this one. Now G and H are open sets. G and H are open sets in the topology on Y. Therefore, F is continuous. F is assumed to be continuous. F is continuous. Therefore, F inverse G will be open. Similarly, F inverse H also will be open because H is also an open set. Right? So these two are open sets, and your G is non-empty. So F inverse G will be non-empty. H is non-empty. F inverse H will be non-empty, and your G and H are disjoint. Therefore, these two sets, F inverse of G and F inverse of H, will be disjoint. Okay, since you can give a number for this. So one implies that F inverse G is non-empty and F inverse H is non-empty, and F inverse G intersection F inverse H is empty, and these are open, in X, and these are open. These are open in capital X. So
sir, please show previous page, sir.
F inverse G union F inverse H. Okay.
Excuse me, sir.
So these are open sets. These two are open sets, non-empty sets. These are non-empty, right? And they are disjoint. They are disjoint. Therefore, this is a disconnection. So therefore, this is a disconnection.
Excuse me, sir.
So this is a disconnection, right? Disconnection. So
Sir,
yes,
F inverse H equal to 5 na, sir?
yes, please.
F inverse H equal to 5.
F inverse H.
In the
Equal to
previous page, sir.
previous page ఒకసారి చూపించండి.
Yeah. F inverse G intersection F inverse H is empty.
Last. Yeah.
Okay. Now these two sets F inverse C. Do you agree? These two
Yes.
sets will be non-empty. Their intersection will be empty. Their intersection will be empty. The intersection of this this and this F inverse G and F inverse H will be empty because of this. Because G intersection H is empty, intersection of these two sets will be empty. Okay. Okay. Hello.
Okay.
Yes, sir.
So these are open sets. These are open non-empty sets, and their intersection is empty. Therefore, and X is written as this disconnection. Therefore, capital X becomes disconnected. What kind of a set is capital X in the hypothesis? Capital X is connected. Capital X is connected. It is a connected set. It is a connected set. But we have got a disconnection. We have got a disconnection for X. Okay. This is a contradiction. This is a contradiction. If you put like this, two opposite arrows, it is a contradiction. Therefore, this arrows because of this. This arrows because we showed that f of x is disconnected. Okay. Therefore, therefore f of x has to be connected. Okay. So we arrived at a contradiction. Therefore, f of x is connected. Okay. See, here I am saying F inverse G intersection F inverse H is empty. Let me show F inverse G intersection F inverse H. This is equal to F inverse of G intersection H. Okay. From set theory, you can show that these two are equal. Okay. And then if there is any common element here, if in case some x belongs to this, it implies x belongs to this. This implies f of x belongs to G intersection H. Okay. Right. If in case this has a common element, say it is x, and then f of x will be in G. Yeah. Otherwise, also you can, even if you don't write like this, you can argue. Without writing this, you can argue. Okay. How? See. If you take an x in this, this implies that x belongs to this, f inverse of G. So f of x belongs to G. Okay. X belongs to this set also. Means f of x belongs to H. Okay. So f of x belongs to H. Yeah. F of x belongs to H. So f of x is a common element in G and H. Right. So you have f of x is in the intersection of G and H. But your G and H are disjoint. Your G and H are disjoint. Okay. So that's how these two have to be disjoint. F inverse G and F inverse H have to be disjoint. Means their intersection is empty. Okay. That's how you get their disjoint sets. So whenever you have a continuous function from a connected topological space into another topological space or the same topological space, then the image of this connected space under a continuous function has to be connected. Okay, means f of x has to be connected. Means continuity preserves connectedness. Continuity. If you have a connected space here, its image also will be continuous. So we say its image also will be connected. If you have a connected space here, its image also will be connected. So continuity preserves connectedness. Okay, this is what you have to observe, right? Yeah. Now let's look at interpolation. It is about it is 8b. It is about totally connectedness. Prove that the components of a totally disconnected space are its points. components of a totally disconnected space or points. Okay. First, let me explain what I mean by component and totally disconnected space. Yeah. First, let us define what we mean by disconnected space. We define a connected space. Okay. If you have a topological space, first let me explain the words involved here. I will explain what I mean by totally disconnected space and then what I mean by component. Then we'll come to prove this. Okay. Yeah. So let us start with the topological space x comma tau, right? We said this is connected, x comma tau is connected if there is no disconnection. X is connected if there does not exist a disconnection. Means X can be written as A union B, where A and B are open and non-empty and disjoint. A intersection B is empty. Okay. This topological space is said to be connected. Is said to be connected if there does not exist a disconnection. If there does not exist a disconnection, this is a disconnection. X is A and B, I'm sorry. Where A and B are open sets coming from tau, they are non-empty and they are disjoint. This should not happen. Okay. Now we define something very close to connectedness called totally disconnectedness. Okay. We say x comma tau is disconnected is a disconnected topological space. It is said to be a disconnected, this is definition. It is said to be a disconnected topological space if and only for every x comma y belonging to capital X and distinct, there exists A comma B in tau such that X belongs to A and Y belongs to B and X is equal to A union B and A and B are disjoint. Okay. Now this a topological space X comma tau is said to be totally disconnected. Totally. Okay. Totally. This is said to be a totally disconnected topological space if and only if for every x comma y in capital X. If you take two distinct points in capital X, members of capital X are called points. Okay. If you take 2 points from capital X, say they are X and Y, corresponding to them, we should be able to find 2 open sets A and B such that capital A is neighborhood of X and capital B is neighborhood of Y and A and B are open sets and these 2 are disjoint and that they form a disconnection for capital X, means their union is capital X. Okay. So that's what this is what is meant by totally disconnected space. So whenever your space x comma tau is disconnected, totally disconnected, then it automatically becomes a connected topological space, isn't it? If you have a totally disconnection, it is connected also because this space is interesting when it has at least 2 elements in that. If you have singleton, if you have see, whenever you speak of connectedness, X is interesting when you have more than 2 points. If there is a single point in capital X, if your capital X is singleton, okay, then one of these has to be empty. Because we want disjointness, one of these has to be empty. Okay, so this cannot happen. You can't have both of them non-empty. You want both of them non-empty and also disjoint. So these 2 conditions insist that a capital X must have at least 2 elements in that. Okay, so connectedness is studied only when you have 2 points in that. Otherwise, you don't study them. You don't study connectedness for such a space. Okay, because these 2 conditions make the disconnection a two-point set. Okay. Yeah. Now, so whenever your space is totally disconnected, you have this kind of a disconnection. So this disconnection, of course, this disconnection depends on the pair of points you take. But you start with a pair of points, and you get one pair of sets capital A, capital B, and that pair of sets capital A, capital B serves as a disconnection for capital X. So that's how every totally disconnected space becomes a connected space. Okay. Now components are largest connected sets. Component that if you take a topological space.
Excuse me, sir.
I'm sorry. If you take a topological space, right? And for example, on R, we are saying intervals, open intervals are connected sets, right? Open intervals are connected sets, right? So, and if you can take, if you can form largest connected set, if the, see this interval, call it capital A. If A is not contained in any other B where B is connected, okay, then we say such a connected space capital A is a component, right? Means it is largest component. It is largest in size. Okay. A containing capital X is said to be component if A is not contained in any B where B contained in X is connected. Okay, right? A subset capital A of X is said to be a component if A is not contained in any larger connected set. Means with respect to connectedness, it is largest in size. Okay, a subset capital A of X is said to be component if it is not contained in any other larger connected set. Okay, if it is not contained in B where B is connected. Okay, so you cannot find a if your set capital A is a component, then you cannot find a superset B of A where B is connected. Okay, so that's what is meant by component, right? And you can also show that if two sets are connected, if in a topological space, if two sets are connected, if capital A, capital B are connected, and if their intersection is non-empty, right? Non-empty, then you can show that their union is connected. Okay, so if in case you have two disjoint open intervals, right? Like this, I call this open interval blue colored open interval B. They have common points here. They have common points in this strip. Okay, and therefore their intersection is non-empty. Capital A, capital B have non-empty intersection, and if you look at their union, that also becomes an open interval. So that also becomes connected, right? So in general, if you have a topological space, if you have two connected subspaces, if their intersection is non-empty, then their union also becomes connected. So if you have two intersecting connected subspaces, out of these, you can generate a larger connected subset, a larger connected space, a connected space larger than these individual connected spaces. Okay, so this is a point to construct larger connected topological spaces, right? Or topological subspaces. Okay, so now we can come to the assertion of this. Components of a totally disconnected space are points. Okay, let us prove this. Components of a totally disconnected space or points. Okay. Yeah. Let us prove this. So let us take a topological space. Let x comma tau be a topological space. Be a topological space. Okay. Right. See, you have to understand one point. If you take a subset capital A of x, and if A is singleton, okay, then this is connected. A is singleton, this is connected. You cannot write this as A union B, where A and B are open, right? In the subspace topology on A, and then they are disjoint. Okay, they are disjoint, and then they are non-empty. You cannot do this, right? if your A is a singleton, if it consists of a single element, then you cannot. Yeah, let me go for some other set here, some G. Okay, because I want to use A union B here. So let me go for some K, right? So if my set K is a singleton where X is coming from small x comes from capital X, so the singleton cannot be written as a disconnection. Means this is a connected subspace. My K is a connected subspace. Why? Can I write singleton as a union of two disjoint open subsets? Can I write singleton X as a union of two disjoint open subsets? Can I do that?
No, sir.
No, because if in case I can write the singleton as this union, say X is in capital A, right? Because they are disjoint, X cannot be in capital B. Okay, and yeah, there is only one point. So this
Sir, sound is very low.
So okay, it is X alone. A K is formed of X alone. So X will be in A or X will be in B. If in case X is in A, B will be empty, and B should not empty. Should not be. This is not. B should not become empty. So that's how a singleton cannot be written as a disconnection. A singleton cannot have a disconnection. Okay. So singletons are always connected subspaces. In a topological space, singletons are always connected subspaces. Right. Thus, singleton in a topological space, this general singleton in a topological space, is connected always. Means, right? It is always a connected subspace. If you take a small x from capital X, and if you look at singleton X, and under the subspace topology, singleton X is connected. Okay. Now, if we can show that the singleton cannot be contained in, it cannot, right? If we can show that there is no y, there does not lie a y in X such that singleton doubleton X comma y is connected, then we are done, right? To show that components are points, what do you have to show? You start with a general singleton. Small x belong to capital X, and then if we can show that if you take any y from capital X, and if you look at this doubleton, then this doubleton becomes disconnected. That's what we have to show. Okay, right? If we want our component to be singleton, we have to show that the singleton is not contained in a larger connected set. Means we have to show that there is no y other than X such that the doubleton X comma y is connected and contains the singleton X. Okay, so we show that this is not possible. Yeah. So
Excuse me, sir.
Yes.
The doubleton X comma Y should be connected, right, sir? You wrote disconnected.
There does not y such that this is agree. There does not y such that this is connected. Agree. I'm sorry. I should not put both no's. I should not want a y such that this is connected. Agree. Okay. Now, let me erase this, and that is the idea behind choosing a y. Yeah, let me start this again. In sense, let me take a y from capital X. Let y belong to capital X be different from small x. Let us take some noise from one of yours, one or more than one of yours phones. Okay, mics.
सर साउंड बहुत कम आ रहा.
Let okay. Let me take a y different addition from small x from capital X. Okay, and now corresponding to this pair, because we are assuming that capital X is totally disconnected, and let it be totally disconnected. No, 1 minute. Yeah, let it be totally disconnected. Okay, let me take this x to be totally disconnected. Means what? Corresponding to this pair of small x and small y. So capital X comma tau is totally disconnected. Means what? There exists open sets. There exists open G comma H belonging to tau such that X belongs to G, Y belongs to H, and G and H are disjoint. Okay, and that capital X is equal to G union H, isn't it? What is meant by total disconnection? What is meant by total disconnection?
Sir, that for every two non-equal points, we can separate them using sets A and B, which are disjoint and open.
1 minute. In book, what is, you look at page 128, for the definition of totally disconnected space. Page 128, right? Yeah. X is said to be totally disconnected. For every pair, you can find a disconnection. For every pair, you can find a disconnection. How did I define total disconnection in the beginning? Did I define? Yeah. It is if and only if there is a disconnection, right? This X is said to be disconnected if corresponding to distinct pair of elements X and Y, you can find a disconnection for X. Then we say it is disconnected. Okay. Yeah. Now let us come here. Now, corresponding to this pair of X and Y, because our space is disconnected, totally disconnected, we can find a disconnection G and H such that X belongs to G and Y belongs to H, and they are disjoint, G and H are disjoint, and that this is a disconnection. Okay, this comes from the definition of totally disconnectedness of capital X. Right? Now, do you have any? Can this be? Now X belongs to G. X belongs to G. Right? X belongs to G implies X belongs to G. And this, okay. Now, X belongs to G. Or let me put it like this. Let me take this Y from a superset, right? Let me take this Y from a superset of singleton X. Okay. And for that, let me take such a Y. I have taken a Y. Let me take this Y from a superset of singleton X. So let Y belong. Okay. What did he say? Here, what did he say? Let Y belongs to X be such that be such that X, it is distinct from Y. Okay. Now, you consider capital Y is equal to doubleton X comma Y. Okay. Right. Now, this is a disconnection. This is a disconnection for X. Now, out of this, can I form a disconnection? Can this be connected? Here, what we want to show? We want to show that components are points. Yeah. So what we have to show? If there is another connected set containing X, that has to be disconnected. That's what we have to show, right? So let us write here. So to show that components are points, right? We have shown that singleton X is a singleton X is connected. Okay, in any topological space, singleton X is connected. And to show that this is a component, we have to show that this is not contained in a larger connected set. Okay, so let us take a larger connected set which contains this. So from that, I'll choose Y. Okay, so let me do that. So let Y contained in X be such that singleton X is contained in Y and Y is connected. Okay, I'm taking a capital Y which is superset of the singleton, X. Okay, I'm taking a capital Y which is superset of singleton X, and I am also assuming that this is connected. Okay, I'll show that this is not possible. I'll show that this right. I'll assume that this singleton X is properly contained in capital Y. I'll show that this leads to a contradiction. Okay, so because I'm assuming that this capital Y is larger than the singleton X, so there will be some small y in capital Y. Let me choose small y from here. So let small y belong to capital Y, distinct from X. Okay, this I can choose because I'm assuming that my capital Y is larger than singleton X. Okay, now from here, can I get can I get that this Y is disconnected from here? What do I have? I have that X and Y, X comma Y belong to capital Y and right? So capital Y is what? Capital Y is Y intersection X. So intersect Y with this, Y intersection G, Y intersection this, union Y intersection H. You intersect Y with this. So by distribution loss, Y intersection G, union Y intersection H. So small x will be element here and small x will be element here, right? So these two are open sets in Y. These are non-empty, and because these are disjoint, these two will be disjoint. So for Y, this is a disconnection. So for Y, this is a disconnection. This is a disconnection. This is a disconnection for Y. Disconnection. Agree? Okay. Your G and H are disjoint. So these two will be disjoint. These two sets will be disjoint, and small x is an element here. Small x is an element here, and small y is an element here. Okay, and these are non-empty, and then these are open sets. These are open sets. G is an open set in tau. So this G intersection Y is an open set in Y. H is an open set in tau. So H intersection Y is an open set in Y, capital Y. Okay, so these two are non-empty disjoint open sets. Therefore, this is a disconnection for capital Y. Therefore, capital Y is disconnected. This is contradiction to disconnectedness. Okay, right? So what we are able to show is that in a totally disconnected space, we cannot have a larger superset of singleton X. For X belonging to small x, we cannot have a larger superset Y of singleton X, which is connected. Okay, it leads to this contradiction. So singleton X is the only connected set. It is the one. It is not contained in any larger connected set. Therefore, singleton X is component. Okay, so that's how your singletons are points. Agree? So I'll repeat. This is a bit involved. Okay. Components of a totally disconnected space are points. Let X, tau be a topological space and be it totally disconnected. Okay. So first of all, I'm showing that for any small x belonging to capital X, singleton X is connected. Okay. You cannot write singleton X as a disconnection because if X belongs to capital A, B will be empty. Okay. Because these two are disjoint. So this is not possible. You cannot write a singleton as a disconnection. Okay. Therefore, singletons are connected. In a topological space, singletons are connected. Now, let us take a larger superset of singleton and assume that it is connected. It is leading to a disconnection. How? From totally disconnectedness, you get two disjoint open sets G and H such that X belongs to, because of this, there will be some Y in capital Y distinction from small x. Okay, this you can choose such a Y other than small x. Now, corresponding to this pair of X and Y, and totally disconnectedness gives you a disconnection G and H. Okay, so that G and H are open, and they are disjoint, and that they form a disconnection for capital X. Now, your Y is contained in capital X, right? Your Y is contained in capital X. So Y is equal to Y intersection X, and X is what? This one. So if you intersect this with capital Y on both sides, Y intersection this is Y intersection G union Y intersection H, right? Now, your X is in G and X is in capital Y also. Your X is in capital Y also. Okay? Your X is in capital Y, right? Therefore, your X is in this intersection. Similarly, your small y is in H, small y is in H, and small y is in capital Y also. Small y is an element in Y intersection H. So these are neighborhoods of X and Y respectively, and they are disjoint because the intersection H is empty. These two sets have to be disjoint. Their intersection has to be empty, and their union is making capital Y. So this is disconnection for capital Y. Therefore, capital Y is disconnected. It contradicts connectedness. So that's how the singleton X cannot be contained in any larger connected subspaces. Okay, so that's how singletons are components. Okay, so that's how we prove this, right? Yeah. Now let me come to question number 10. Question number 10. Pen. Question number 10. Define an open map. Define an open map. Define an open map and give an example of an open mapping. And give an example of an open mapping. And give an example of an open mapping. Okay. Define an open map. Right. What is an open map? If you have two topological spaces, right? If you have two topological spaces, then what is an open map? In functional analysis, of course, in your functional analysis course next year, you will be studying open maps. An open map is a map which takes open sets onto open sets. If you have a G contained in X, and if your G is open, if f of G goes to, f of G is also open, okay, then we say this map F is open. If F takes open sets onto open sets, then we say this F is open, an open map, okay? An open map is a map which takes open sets, my handwriting is very bad. Okay, the two writing on this slate is very difficult. An open map is a map which takes open sets open subsets, open sets onto open sets, onto open sets. Okay, so if f is a function from x into y, you take a general open set here, let it be G, and look at f of G. If f of G is also open, and if this is true for each and every G open, and then we say this f is an open map. Okay, so in other words, openness, f is open means your f inverse is continuous. F is open means if your f inverse is continuous. F inverse is continuous. You may recall f is continuous if and only if f inverse is open, right? F is continuous if and only if f inverse of G, if f takes x into y, if this is continuous, it is equal to saying if you take some h here, okay, if this is open, if h is open, right? If I take topology eta, if h is coming from eta, if you look at f inverse of h, okay, f inverse map, you look at f inverse of h, okay, and if this is open, and if this is true for each and every h, then we say, yeah, it will be true. If f is continuous, for every h coming from eta, f inverse of h will be open. Okay, continuity is equal to saying that f inverse takes every open set onto open set, means your f inverse is open map. Okay, so if f is continuous, f inverse will be open. If f is open, f inverse will be continuous. If you take f here, you have to take f inverse here. If you take f inverse here, you have to take f here. Okay, yeah, this is what we mean by an open map. Let us give an example. Okay, to see a trivial example, right? A trivial example is the identity map. A trivial example for function C is identity map. Okay, you take your f to be identity map. What does identity map do? It takes a set x. It takes a set. Actually, okay, it's a kind of right abuse of notation. I'm not taking points here. I'm looking at the sets here. Okay, so if you take G here, you have to look at f of G, right? What if I'm taking my f to be the identity map? So what is identity of G? Identity of G will be, right? Identity takes G onto ID of G. So what is identity of G? What is the image of G under identity function? It is G itself. Okay. If you G, and I will take my Y also to be x comma tau, right? I'll take the same topological space as the codomain, right? Now under this map, if something is open here, its image is also itself, and therefore it also will be open in the codomain topology. Okay. So this is a trivial example. If you take your G to be open, under the identity function, the image of G is G itself, and this is open. You are assuming G is open, and you want to check whether identity is also identity of G is open. Identity of G is G itself, and it is right by default. It is an open set. So and this, you are taking the same topology for the codomain. It will also be open in the codomain. Okay, so this example for an open map. The identity function taking a topological space into itself is an open map. The identity map from a topological space, into itself, is an open map. Okay. This is a trivial example. Yeah. Next is question number 11. Let x comma tau be metric spaces. Let x comma tau.
Previous page ఒకసారి చూపించండి.
Yes, please.
Previous page ఒక్కసారి.
Okay. right? Okay.
1 minute, sir.
Sir, sound is very low. It's not in my hands. What can I do for sound? Sound is not in my hands. I don't know how to adjust all those things. Okay, we have some more. Yeah. Okay. Next is question 11. Right? Question 11. F is a mapping from X into Y. X comma Y are metric spaces. X comma Y are metric spaces. Right. Okay. Oh, I want to move this. Okay. Let X comma Y be metric spaces, and then prove that Xn converges to X, and let this be continuous. Let F be continuous. Let this be a continuous map, and prove that Xn converges to X in X in capital X implies f of Xn converges to f of X. F of Xn converges to f of X. In fact, the converse is also true in Y. This happens in Y. Okay. Let F map a metric space X D into metric space YD dash. Okay. Be continuous. And then if a sequence Xn converges to X in capital X, then show that the image sequence converges to the image. Okay. Means continuity preserves convergence. Continuity preserves convergence. Right? How we can prove this? The converse is also true. In fact, if you have this, you can show that it is continuous. First, let me prove this. So, what is meant by we are taking an X in capital X. So let us start with the small X in capital X. Okay, and we are assuming that F from capital X into capital Y is continuous. What does it mean? Given epsilon greater than 0. What does it mean? What is the definition of continuity? Given epsilon positive, there exists a delta positive such that d of X comma Y is less than delta implies d of, what is the definition of continuity? Modulus of X, if your capital X is R, if F is mapping some R into R, okay, and if A belongs to R, when do you say F is continuous at A? F is continuous at A, F is continuous at A, if and only if for every epsilon positive, there is a delta positive, such that modulus of X minus A is less than delta implies mod F of X minus F of A is less than epsilon. Okay, this is the definition of continuity for a real valued function of a real variable. Okay, if F maps R into R or a subset of R into R, and if small a belongs to R, then we say F is continuous at A. If and only for every epsilon positive, there is a delta positive. There exists a delta positive. Such that modulus of X minus A less than delta plus mod F of X minus F of A is less than epsilon. You convert this into the terms of metrics. Okay, so this should be replaced by the metric on capital X. X and A come from R. Okay, this domain set. So d of X comma, I am in place of right A, I am taking Y. Okay, in place of A I have X. So in place of X I will take Y. So I'll have d of X comma Y less than delta implies. Here we have to take F of X and F of A. The distance between Fx and Fa, that is d dash of F of X comma F of Y is less than epsilon. You replace modulus of x minus a. This is the distance between x and a. Replace this by the corresponding metric between x and a. That is d of x comma y less than delta. Right? In place of a, I'm taking x. So, right, this is continuity at a. Or if you want continuity at x, if you want this to be your x, you replace a by x and x by y. Okay. So what do you have? So if this is this is small x. So for x comma y less than delta plus f of x minus f of y is less than epsilon. Okay. For x is f is continuous at x in R, if only for every epsilon positive there is a delta positive z, modulus of x minus y less than delta implies mod f of x minus f of y is less than epsilon. Okay. Replace this by metric d of x comma y. Okay. Replace this by metric d dash of, right? Your f of x, f of y are in y, capital Y. So you have to take this metric, d dash metric. So d dash of fx fy is less than epsilon. Okay. This is generalization of this one to metric spaces. Okay. So yeah, I can erase this now. If you remember the definition of continuity for real valued functions of a real variable, you can write down this one for general metric spaces. Okay. Now, yeah. Now let us use this. What is the meaning that xn is converging to x? Xn is a sequence in x. Okay. So xn is converging to x in capital X implies what? What does this mean? For f, okay. Now for this positive number delta, okay, I'll ask for a sufficiently large n. So what I have for this delta positive, for this positive delta, there exists an n naught belonging to capital N such that for all n greater than or equal to n naught, the distance between xn and x can be made less than delta. Okay. What is the meaning that xn, the sequence xn converges to x in x, xn's are coming from capital X, and that if you take any positive number epsilon corresponding to that, there will be a natural number n naught, right? This set of natural numbers. N naught is a natural number, fixed natural number, such that whenever the suffix n is larger than n naught, the distance between xn and x can be made less than this arbitrary positive number. Okay. So now you use this n naught. So for n naught belonging to capital N, right, and n greater than or equal to n naught, you have d of xn comma x is less than delta. Okay. So if I take these n's which are larger than or equal to n naught, so this is less than d of xn comma x is less than delta. Now in place of y I can take xn. So here I can take f of xn. So if I call this 2, so this implies d dash of f of x comma f of xn is less than epsilon by 2. Okay. Now in place of y I want to take xn. D of xn comma x is same as d of x comma xn. I can interchange x and xn. Okay. So in place of y I can take xn. In place of y I have to take xn. So in place of y, I have to take xn. So fxn comes here, f of x comes here. So from this step, I'll get that the distance d dash between f of x and f of xn is less than epsilon. Okay. So I started with an epsilon positive, arbitrary, and corresponding to that, I can choose an n naught such that this n naught. Okay. The n naught coming in this from this convergence. So for this n naught, for whenever n is greater than or equal to n naught, right? I have the distance between distance between fx and fxn, or fxn is less than epsilon. This implies that your f of xn converges to what? This converges to, if your xn converges to x, you have d of xn comma x is less than delta. Okay. What does this mean? F of x converges to
fx.
f of x, isn't it?
Yes, sir.
Yeah. So whenever you have a continuous function from a metric space into another metric space are the same, and if in case you have a sequence of x's converging to an x in capital X, then if you look at the image sequence of images, that has to converge to the image of this limit x. Okay. Means continue preserves convergence. If your function is continuous, f of x will be converging to f of x. Means it preserves the convergence. Continuity preserves the convergence of sequences. Okay. This is the answer for this question, and the converse is also true. Whenever for a sequence of x's converging to x in x, if f of x converges to f of x, then you can show that f is continuous. Let me prove that part also. Okay. Of course. Yeah. This is not for the right. The answer is over here. The answer is over here, but for your extra knowledge, I'm doing the converse part. Okay. So let for x n converging to x in x, right? F of x n converge to f of x in y. Right? Now, this is a statement. This statement implies that f from x to y is continuous. Okay, this is the assertion. This is the assertion. Okay, proof. I want to prove that the converse of this is also true. Means, see, this has implied this one. This hypothesis has given us this. Now, I am making this hypothesis. I want to obtain this as conclusion. Okay. Yeah. So yeah. So so let us assume this. Let for xn converging to x in x imply f of xn converges to f of x in y. Okay. I'm taking d here and d dash here. I'm taking d here and d dash here as metrics. Okay. Now I claim f is continuous. F from x to y is continuous. Okay. What is the definition of continuity? This is the definition of continuity. Given epsilon positive, there is a delta positive, so that g of x comma y less than delta m plus d dash of f of x f of y is less than epsilon. This is the continuity at x. Okay. So yeah, I'll take a small x here. Yeah. Let me take a general point x from capital X. Let small x be a general point in capital X. So f is continuous. We want to show that f is continuous. So claim f is continuous at x. Okay, means I want to obtain this. One. Suppose it is this. Suppose f is not continuous. Negation of this is true. What is negation of this? There exists for every replace for every by there exists, and replace there exists by for every. There exists an epsilon positive such that whenever delta is greater than 0, there is a y satisfying this, but this fails. That is negation. I'm saying again, replace this by there exists, replace there exists by for every. So negation of this is what? There exists an epsilon positive such that for every delta positive, there is a y in this epsilon delta neighborhood such that this fails. Okay, this is greater than equal to this. So I have yeah. So claim. So proof. Let f be not continuous at x. What is the meaning of this? Means I have to take the negation of this, negation of 2, this statement 2. Okay, so this is equivalent to saying that for there exists an epsilon positive such that for every delta, I will take n here. For every n, for every small n belonging to natural numbers, out of natural numbers small n, my natural numbers are positive numbers. So I can get a small number 1 by n as delta. I'll take delta equal to 1 by n. Okay, I'll take delta equal to 1 by n. So for every natural number n belonging to n, there exists a yn in capital X such that d of x comma yn is less than 1 by n, but d dash of f of x comma f of yn is greater than or equal to epsilon. Okay. See here, I'm writing the negation of 2. So there is this epsilon positive as that for every delta positive, in place of delta, I will take delta equal to 1 by n, where my n is any natural number. I will take a general natural number, small n. Corresponding to that, I will take delta to be 1 by n. So n is positive number, positive integer. So 1 by n will be a positive number. Okay. So I'll take delta equal to 1 by n. Corresponding to this delta equal to 1 by n, there will be some y, call it yn. It depends on this n. Okay, call it yn. This is true, but this fails, greater than or equal to comes here. So that's what I'm writing. There is an epsilon positive such that for all n belonging to natural numbers, there exists a yn such that d of x comma yn, d of x comma yn is less than delta. Delta is equal to yn, 1 by n. Delta equal to 1 by n. But this is true. Negation of this is true. Means this is greater than or equal to d dash of f of x comma f of y. D dash of f of x comma my y in place of y, I am taking yn. D of y, f of x comma yn. Okay, f of x comma yn is greater than or equal to, or right? You have to replace this by negation. It's opposite. The other positive complement that is greater than or equal to epsilon. Okay. Now for this kind of a sequence of yns, okay, as your n varies, you'll be getting yns. So this sequence of yns, and because of this, the sequence is converging to x. The sequence of yns is converging to x. Okay, so you have got a sequence of yns converging to x, because as n goes to infinity, 1 by n goes to 0. So you have got a sequence of sequence yns from capital X, which is converging to x. And how about this? The distance between this is a positive epsilon, right? This is a positive epsilon, right? If this is 0, yeah, means see, x is fixed quantity. F of, I should write like maybe vertically I should write. Okay. This is f of x. Can I write this way? Yeah. This is f of x. This is some f of x value. Okay. F of yn value. Right. So this is some f of x value. This is f of x value. And if this distance is epsilon, if this is epsilon. This is f of x minus epsilon. This is f of x plus epsilon. This is f of x minus epsilon. This is f of x plus epsilon. Okay, this point is f of x plus epsilon. This is f of x minus epsilon. So this fyns will be somewhere here. Fyns will be either here or here. Okay, right? The distance from fx to fyns. These are fyns. Green numbers are fyns. Okay, they are the distance between these two, fx and fyns. Right? For a fixed n, yn is a point here. Yn is a point here. Okay, so for fixed n, yn is a point here. So f of y. This is f of yn. Okay. For fixed n, f of yn is a point. So the distance between fyn and fx is greater than or equal to epsilon. It is larger than this. Okay. So they don't come closer. If f of x and f of y's have to come to f of x, they should come arbitrarily close, like this. As n becomes small, large and large, this turns to 0. So this will be coming close. But here, they never come close because if the distance between fx and fn is more than this. Okay, they are apart. They can never come closer than epsilon. They are always at more than at a distance of epsilon. The distance between them is more than epsilon. The distance between them is never less than epsilon. So because of this, you have a sequence yn converging to x, but f of yns are not converging to f of x, are not converging to f of x because of this. Okay, so you could construct a sequence of sequence yn in capital X such that yn converges to x. This you have, but this you don't have. Okay, this you have, but this you don't have. The corresponding to the images f by n's, they are not converging to fx. Okay, so it is the hypothesis. If a sequence is converging to x, the image sequence must converge to image of the limit here. But it is not happening. You could construct a sequence here, yns in capital X, but f of yns are not converging to f of, right? Here, yns are converging to x, but f of yns are not converging to f of x. Okay, so this is violation. This is a contradiction to this hypothesis. To this assumption, this is a contradiction. Okay, therefore, your claim is false. This false claim that f is continuous, f is not continuous at x. This is false claim, false assumption. This false assumption has led us to contradiction. So therefore, this assumption is wrong. Therefore, your f is continuous. Okay, so that's how the preservance of convergence will lead to continuity of f. Okay, so in between metric spaces, continuity is same as preservance of convergence. Okay, continuity should be viewed as a tool that preserves convergence. Okay, so with that, I would like to stop. Right, for the next class, let me see what else I can discuss. Right, okay, yeah. Any suggestion? Hello, I would like to stop here. It is 6 o'clock.
Sir.
Yeah, can I stop here? Any advice?
Yes, sir.
Any advice or remark or comment or anything?
Sir, I have a doubt.
Yeah.
Could you give an example of a totally disconnected space?
Wait, let me try. Is it Harshvardhan?
Yes, sir.
You are the guy we want the most. Okay. You want? I was thinking of this. Of course, R is not totally disconnected, I think. Okay. You want a topological space which is totally disconnected, right?
Yes,
totally
sir.
Disconnected. Let me try. Totally disconnected. If I go for the discrete topology, yeah, can't I have it? If I go for the discrete topology, okay. If I take any two distinct points, right, then so my separation is capital X equal to singleton X and its complement. Okay, right, this will do, no? So this is in discrete topology gives you totally disconnectedness,
Right.
isn't it?
Yes, sir.
Agree?
Yes, sir.
In discrete topology, let it have more than 2 elements. Okay, let your X have more than 2 elements. You have discrete topology on that, and then you start with a distinct pair of elements X and Y. Okay, you want a disconnection for X. It is singleton X union its complement. Every set is open set here. This is open, right? And Y will be here and X will be here. And they are disjoint. So this is a disconnection. So your space is totally disconnected. Agree?
Yes, sir.
Agree. This is, yeah. Right. Of course. In the next questions, actually, you're asked to construct a metric with discrete topology.
Okay, sir.
Okay. Yeah. I was I think once I said about the discrete metric. Do you know about discrete metric?
Yes, sir. I think whenever
for X equal to Y, it is 0. F of X comma Y is 0. Otherwise, it is 1.
Yes, sir.
Otherwise, it is 1. This is called discrete metric. Okay.
Right.
The topology comes out of this is a discrete topology. The topology
Okay,
that comes out of this is discrete topology. Okay.
Right, sir. Right.
So this metric generates discrete topology. So that becomes totally disconnected, right? Okay.
Right.
Anything else?
And sir, I have understood that for totally disconnected space, components are singletons.
Yeah.
But is there any example where components are, let us say, intervals or doubletons?
So it should not be totally disconnected.
It should not be
So,
totally. Yeah.
Yeah. So we want a space which is not totally disconnected. Okay. Totally disconnected. I don't know. I have to look. Okay.
Okay,
Maybe
sir,
in
no
the
problem.
next class I will tell you, or
No
through
problem.
WhatsApp. Okay. So
Yes, sir.
your doubt is there a topological space which is not totally
Where the
disconnected?
components are not singletons, just usual
Right.
intervals.
Okay. In totally disconnected topological spaces, components are singletons. So I have to construct a space which is not totally disconnected. In that, the components may be having more than one point.
If one,
Okay.
one. Yes, sir.
I'll try and inform.
Sure.
You. Okay.
Yes, sir. I will send you a
And
message.
how about this? See, in discrete topology is not interesting. There is only one open set here. There is only one open set in discrete topology, right? No, there is only one non-empty open set in discrete topology. It is not interesting. So, okay, I'll look into the literature and inform. Okay?
Sir, I was thinking about the real number line. If we take all the intervals a comma b, which is semi-open, can we say they are components?
Please say again what you are saying. Semi-open. Semi-open.
Can the components be semi-open intervals?
Yeah, it's an interval. On R, you are saying no?
Yes, sir, on R.
Yeah, it's an interval. No, it is an interval.
But semi-open.
Semi-open intervals are also interval. What is the meaning of interval? If x comma y belong to some a, x less than some c less than y must be having you c belongs to a. Okay, this is what is meant by an interval. Capital A set to be interval is this property is satisfied. All these things satisfy this condition.
Okay,
semi-open intervals are connected.
Okay, sir.
Of course. If you, this is not a component, because see, there is another property of connected topological space. If A is connected, A closure will be connected. A is connected, A closure will be connected. So you have to look at right. A closure will be connected. It is a property. It is a proposition. Okay. If A is connected, A closure will be connected. Okay. So these are right. For example, the closure of open interval. The closure of open interval is closed interval, and closed interval is larger than open interval.
Yes, sir.
Closed interval, right? Closed interval probably contains open interval. So this is not a component. This may be a component. Okay. We have to check. Right. Okay,
sir.
Yeah. I will verify and tell you. Please give me time.
Yes, sir.
Right?
Sir.
Through WhatsApp, I will try to tell, or in the next class.
No problem, sir.
Okay. Anything else?
That's all, sir.
Okay. घर जाएंगे. Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Goodbye. Bye bye.